Well, welcome to Interface and our next ForceLeaders event. We want to thank everyone for joining today. We are taking our multi-axis conversation that we started actually about 1.5 years ago and elevating that with some additional information, questions that people ask, as well as exciting new products that we'd like to feature in this discussion. On board today, we have our resident experts in solutions, our solutions engineers and custom solution specialists, Keith Skidmore and Ken Bishop. We're very excited to have you here today to share with us some really exciting information about where multi-axis is headed and the different types of instrumentation and accessories that support that. So as we get started here today, just please note that there is a chat feature available that you can add any questions to. We'll try to address those near the close of the event when we do our frequently asked questions. This event is recorded and we will be sharing this after the event with all the participants, as well as posting this on our website and YouTube channel. And again, thanks for joining us. So to kick things off, let's go ahead and hand this over to Keith and Ken.
Welcome, everyone. Glad you're joining us. Next slide, please. So these are the topics we're going to cover today. Our 3- and 6-axis multi-axis sensors, why use the BX8, benefits of the BSC4, what about mounting plates, introducing new force plate options, outlook on multi-axis systems, applications and use cases, and FAQs. Next slide. Why use 3- and 6-axis sensors? Well, number one, best reason is to get more data. And we can do a lot with more data. We'll talk more about that through this presentation. Maximize your return on your investment in the test. So if you're running the test, you might as well get more data out of that test since you've already spent the money on fixturing it and running it. And compact and less complicated than using multiple single axis sensors. So basically you put it in place, you could get 3 axes or 6 axes measurements without finding ways to mount 6 different sensors or 3 different sensors. Next slide. So our 3A series multi-axis sensor, this is a 3-axis load cell. It has equal force in Fx, Fy, and Fz. It's got a square shape, low height, and low crosstalk, and pretty easy to use. Next slide. Our 3AR series is a round shape sensor, still with 3 full bridge outputs, Fx, Fy, Fz. Fx and Fy have the same capacity. Fz has a larger capacity. And you can see this one caters to, doesn't go as low as our 3A series, but goes quite high, matching our other 3A series. Next slide. Our 6-axis series, we have our standard capacities, and those go from 50 Newton force to 100 kilonewton force. And in torque, it goes from 1 Newton meter all the way up to 10K Newton meter. Again, compact in size. These use what's called a 36-term coefficient matrix, coupled with our BX8 instrument, which Keith will explain a little bit later. Makes it pretty easy to use. It has low crosstalk, and you get, of course, measurements in Fx, Fy, Fz, Mx, My, and Mz. Next slide. So our high capacity 6-axis load cells have force range of 50 kilonewton up to 800 kilonewton force. And in torque, it goes from 10K Newton meter up to 40K Newton meter. These use the 72-term coefficient matrix, and requires the use of 2 of our BX8 instruments to do the processing. Again, low crosstalk, but opens up the possibilities of doing large capacity testing, which I think makes us unique in the industry. Next slide. Our 6ADF is a DIN flanged arranged 6-axis load cell. Basically, it's a DIN EN ISO 9409-1, and it's used in robots and allows you to put the sensor in line with your application. And a nice feature of this is it has a through hole in the middle. So sometimes you'll need to run cables, etc., through the center of the load cell. This one allows you to do this. Next slide, please. And hand it over to Keith.
Hello, everyone. We'll talk a bit about our model BX8 instrument. So the BX8, 8 stands for 8 channels. 6 channels are required for the 6-axis sensors. Gives you 2 extra channels for other things. The channels are all synchronized, means they sample simultaneously. Very high sample rate, 48,000 samples per second. Again, synchronous, so all channels are being sampled at 48,000 times per second. Can do internal calculations of the load values for 6-axis sensors. It can actively scale its analog outputs per those calculations. High resolution, has a connection to the PC and includes graphing and logging software for data analysis and collection. Next slide, please. So, high-speed synchronous sampling. It's important. These are millivolt per volt output sensors. The 6-axis sensors, you actually run some math. You take all 6 signals and run them across a coefficient matrix. And it's important that all of those signals are sampled at the same time, especially for dynamic measurement. So if the load is changing and you're sampling the channels at different times and you're running your math on all those signals as if they were taken at the same time, you can get very, very large errors and wrong results. So it's very important that be sampling fast enough and synchronously. Also, it has very high resolution and a very low noise floor. This is important. These 6-axis sensors have somewhat low output, certainly on certain load combinations. And so it's important to be able to resolve very low level signals, which BX8 does very well. Includes our BlueDAC software, which makes it very easy. You can view the data, you can log, you can have graphs or displays of the data, and you can then log it to a PC. Has data analysis. You can open up the files and explore them. In the software, you can export to Excel or whatever. Also, there's a licensed version. The software is free. There's a BlueDAC Pro, which is new, which adds the ability to do math scripts. And that's basically, you can add channels that are math channels, and you can do all kinds of complicated math on the signals if you like. Very interesting, opens up a wide range of potential. Also, it's possible to take multiple BX8s and synchronize them together. And this is useful for the large capacity 6-axis sensors, like Ken mentioned. They've got a 72-term coefficient matrix. It's basically a 6x12 matrix, and there are 12 signals. And so need to use 2 of these to get 12 input channels. They can be synchronized together, so they're sampling synchronously. Very much compatible with LabVIEW. Our BlueDAC software is actually written in LabVIEW, so these boxes are quite compatible, and we have VIs and programming examples for that. Next slide, please. So use cases. Obviously, 6-axis sensor. You can use multiple 3-axis sensors with these, and the connectors on the box accommodate these quite well. You have to know what you're connecting, but we'll put single connector on this 3-axis sensor that plugs right in to the BX8. Also, you can combine other sensors with these. So you could say a 3-axis sensor, you could have an encoder for measuring position, or you'd have temperature, either a thermocouple or an actual temperature sensor. You actually hook strain gauges up to the BX8. And so it has strain gauge input channels, just like a full bridge, except has the ability to do bridge completion inside the box. And that's either for half or quarter bridges. And it can also do that with 3 different types of, or 3 different completion resistors. Sorry, stumbled there for a little bit. EtherCAT connectivity, CAN bus, CAN open connectivity. So if you want to network your devices, this system works well with that. And of course, as I mentioned, the BlueDAC software. Next slide, please. We're also doing some pretty neat things with BX8s combined with Raspberry Pi. We've got a picture of a box here with the Pi mounted on top. It's using a USB connection to the Pi, and then once the data is in the Pi, you can write software to do whatever you want with it, which is pretty interesting. In this case, it's being used to do an Ethernet conversion. This is an EtherCAT box. The EtherCAT and Ethernet aren't necessarily compatible in the same box, so we're using the USB to Ethernet conversion through the Pi, and the box is natively EtherCAT. You can also see to the right of that is another package of the BX8. So it either comes in the black box or this environmentally sealed box, as you see on the right. That box, we've mounted a Pi inside the lid. And again, you can use that for all kinds of things. It could be a standard standalone data logger. Again, with custom software in the Pi, you can do all kinds of standalone things, event monitoring, triggering, really whatever you can think of. Next slide, please. BSC4. So the BSC4 is the BX8's little brother. It's a 4-channel device. It's not as sophisticated. It's quite nice though. It's easy to use. Has millivolt per volt inputs, which works well with these 3-axis sensors. It also has voltage inputs, and it's user selectable. And then you can also have strain gauge with bridge completion. It's obviously for use with our 3-axis sensors, has a connector on it, so you can connect the load cell right up to it without having to monkey around with different connectors. Can basically also be used with individual sensors too, up to 4 millivolt per volt or VDC output sensors. There's 2 varieties. There's a BSC4A, which stands for analog, and that has analog output, so 1 output per channel, either plus or minus 10 volts or 4 to 20 milliamps, and those are selectable. Or there's a digital version, BSC4D, has USB output, and that includes a BlueDAC software for logging and graphing. Next slide, please. Advantage of the BSC4A and D is compact, so you can certainly use 3 or 4 independent signal conditional single channel ones, but these are quite nice. They have a connector on it, so you plug your 3-axis sensor in, you get 3 outputs, you're good to go. Also, they're more cost effective than buying individual amplifiers. And then of course the digital version comes with our BlueDAC software, and it's LabVIEW compatible. We have a number of customers who've written their own LabVIEW programs to work with this. It also have digital I/O, so you can say command to start logging via trigger if you're using the digital version, or you can have threshold set where you have active, say, set point outputs, or a tear or whatnot. Next slide, please. So again, 3-axis sensors, good case for the BSC4. You can also add an additional sensor, whether that's millivolt per volt or a voltage output sensor. If you're saying applying a test load with 1 channel, you can have up to 3 strain gauges hooked up, either full bridges, half bridges, quarter bridges. So say you're strain gauging a part and applying a test load, the BSC4 could be useful. Of course, multiple single axis sensors. And you can actually use multiple BSC4Ds together, and they can be synchronized via their I/O ports, so there's all sampling simultaneously. Next slide, please. New BX6. So this wasn't in the table of contents, but we threw it in here. It's a pretty cool new little device. You can see the picture. That's actually a standard paperclip, so pretty small, and that's a micro SD card. So the BX6 is wireless Bluetooth. It's quite small, has 7 channels, so 6, say, sensor channels plus an encoder, 2-channel pulse input for the 7th channel. Can do either low energy or classic Bluetooth. It logs data to the SD card. It's also completely compatible with our BlueDAC software. And it also is a 6-axis compatible in that you can hook up a 6-channel, 6-axis sensor. You can load the matrix internally. It'll do the matrix math and then digitally output the forces and torques or store them to the SD card as actual calculated values. Next slide, please. So more on the BX6. It's useful with a rechargeable battery, although you can power it off of line power as well. Has built-in battery charging circuitry. Says got millivolt per volt inputs, can also be used with voltage inputs, counter frequency, you can do RPM or angle input. Does bridge completion. So one use case is pretty small. You could mount it to something that's moving. If you're, say, strain gauge an axle or whatever, you could actually hook up to 6 strain gauges up to it, do bridge completion, and then you could, say, broadcast that data via Bluetooth or just store it to the SD card and pull it later. And he does that simultaneously too. So it's broadcasting data and storing to the SD card. So in case you, say, lost your data connection for some reason, the data is still being stored to the SD card. Also, it samples up to 3,000 samples per second on a single channel. If you're splitting processing, say, the 6-axis data, it's up to about 2,000 samples per second. Next slide. TAD's capability on channel 1, so you could, say, identify what sensor is connected to it. It's got set point outputs, so you can sit there and act. It can close the digital outputs at certain threshold values, for example. Has real-time clock so that your data has the actual timestamp. Say digital inputs, you can, say, start the logging via an external trigger, or you can zero, and it's also completely compatible with LabVIEW, and we've got the drivers and PIs and things to help with that. Next slide, please. Mounting plates. What about mounting? So all of these sensors, all sensors really, but the 6-axis in particular, they should be considered as a system. And so correct mounting practices are extremely important. So the system includes a sensor plus the mounting hardware. And deflections in the system can introduce errors and apparent crosstalk into the sensor, into the measurement. So it's important to consider mounting. Plates should be stiff enough. It's hard to define what that is, but you can imagine a flimsy plate that's square, mounted on its corners. When you load the system, the plate would bend a lot, and you'd get all kinds of crazy, say, off-axis loading. And basically what you're trying to do is emulate how the sensor was calibrated, right? So if it was calibrated on stiff plates, the characteristics of the calibration are duplicated by duplicating that type of arrangement. So if you mount it to, say, flimsy plates, you get a lot of bending. That's going to create errors due to conditions that are different from how it was calibrated. One thing to note is the mounting instructions are specific for each unique model, so you have to pay attention to the data sheets and the drawings. They're all have similarities, but the specific call outs for what the say locating features are may be different for each model, even within a given series. So next slide, please. So we do publish mounting instructions, and they would include things like this table, which gives you the type of hardware that's used, recommendations for the class of hardware, the mounting torques, the dowel pins in cases of sensors that have dowel pins, etc. These are available on the web. Also, our application engineers can provide this information. Moving on, please. So 3-axis mounting. We have assembly instructions. You can see here a few examples. On the left, we have a sensor that has 4 threaded mounting holes in the top surface and 2 dowel pins. They should be used. These sensors have the ability to take FX, FY, obviously. You don't want the plates to slip. The dowel pins help with that. Also, they help with aligning the axes. On the bottom, too, there are a couple dowel pins. And you should also observe the mating surfaces. Usually they may be shown with hash marks or labeled, but there's a live end, a dead end. There's a little, on the 3-axis, there's little, say, feet on the bottom that have to be mounted, and then a center surface. See to the right, or in the center, basically is a bigger 3-axis. You can see this 3-axis now has more dowel pins. These ones actually have 5 dowel pins, and 4 mounting bolts for the tops live surface, and then 4 for the dead end. Basically, the dowel pins again are trying to keep the sensor from slipping in the assembly. Also for locating, you want the X and Y axes clocked properly. To the right is a round 3-axis sensor, could be a 6-axis sensor as well. These are mounted via the rounding surfaces. You definitely don't want to load them, say, in the middle, and they'll have dowel pins, they may have pilots, and they'll have mounting bolts, and you want to use all of these features. Moving on, please. Again, 6-axis, we've got tables that show all the different mounting torques and the type of hardware and the construction, these aluminum or steel. It's important that the mounting plates be similar material if possible. Next slide, please. So these are some examples of mounting hardware. The one on the left, you can see we have a little red X through it because this actually turned out to be a not optimal design. So the idea is when you mount to the sensor and then you apply your loads, you want the sensor to sort of deflect uniformly. You don't want local deformation, say, at the sensor surface. And this fixture on the left actually allowed sort of kind of a weird bending to go on at that interface to that plate section that's then bolted to the load cell. On the right, you can see an example of a fixture that would be better. See, it doesn't have any sort of weak spots to allow sort of non-uniform bending. Next slide, please. So these slides show sort of examples of where you talk about local deflections. The idea is to apply the force equally across the surface, have your mounting plates and everything kind of bend evenly. You can see this where there's a lever basically applied to a plate that's bolted to the load cell, and where it's red, you can see areas of much higher strain. And on the right, you can see sort of top view of that same arrangement, and where it's kind of red, the diagram, you see that's local bending, non-uniform deflection. And these sensors have strain gauged, say, beams below the plate, and those beams need to be loaded uniformly. And so when you do something like this, you're actually kind of bending the top plate, and it's creating non-uniform loading, which definitely is not how the sensor was calibrated. So if you're going to try and get good results, you need to kind of emulate the way it was calibrated, and certainly wouldn't calibrate it with something like this. Next slide, please. So again, each sensor has unique features that need to be observed per its data sheet and the specific drawing. Again, it's even within the same series, they may be different. So 6A40 is a small 6-axis. It has mounting feet. The hash marks are where they would mate and touch your mounting surface. There's 2 of them that aren't hashed. That's a mistake. They should all be hashed. Those should all be touching your mounting plate. And then there are mounting bolt holes that are, say, between those feet, and then there are dowel pin holes that you can see. There's one in the center of one of the feet, and there's also a pilot. And a pilot, you can tell on a data sheet or a drawing, there'll be a circular feature that has a tight tolerance assigned to it. And usually the data sheets and drawings don't have individual tolerances on all the dimensions. So when you see a specific or a single dimension has a tight tolerance, usually that's for a reason, and it's in this case would be the pilot. That's how you tell where the pilot is. On the right, we have a larger 6-axis sensor. It has feet as well, but you can see the bolt circle is actually on the feet, and the dowel pins are on the feet as well. And that one has a pilot too. You'll note though on the 6A110, the pilot is the ID of the feet, whereas on the 6A40, the pilot is the OD of the feet. So again, important to observe these things, and they can be determined by looking at the data sheet or the drawing for the tight tolerance, called out like as an H7 or a +0 minus something. Next slide, please. So this is an example when you're bolting to these sensors. A lot of times, obviously your item doesn't necessarily have the same bolt pattern as the sensor. So this is an example, say, of a sandwich plate arrangement. So you can bolt the sensor to the plate, and then bolt the plate to another plate, and that other plate bolts to your assembly. And when doing something like this, they should be suitably thick and of a similar material as the sensor. You imagine if these pieces are all different materials, they'll expand and contract at different rates during thermal cycling, and that can affect the measurements because you get basically apparent strain in the sensor, or EF strain, which would seem to be due to loading, but really just due to this generated forces due to the expansion. Should be flat and smooth When you bolt the sensor down, you don't want to distort it during mounting. Next slide, please. Force plate options. These are pretty exciting. Something that we've been working on, somewhat new to interface. This is a picture of a quite large force plate. Has 4 3-axis sensors bolted between plates. We'll define a force plate as a system of multiple multi-axis sensors mounted between 2 plates. So something like this has 3 signals per sensor. There's 4 sensors, so 12 signals. Works like a 6-axis sensor. Basically, you end up with a 72-term coefficient matrix and multiply across that to get your fx, fyx, fz, mx, my, mz. Why would you have a force plate? Well, one thing you can imagine, you can get larger capacity. So if you take the largest 3-axis sensors, mount them between a plate system, all of a sudden you've added the total forces together, so you end up with a larger capacity system. You can also react quite larger moments with a system like this. Imagine a single 6-axis sensor in the middle, or even a 3-axis sensor in the middle. There's a limit to how much bending moment it can take. Now you spread these sensors out to the corners or the outside of a plate system, and the lever arm goes up. You can react much higher moments this way. The sensor system, includes the sensors and the plates, and so the results are definitely dependent on the characteristics of the plates, the system, and also what's bolted to it, how it's loaded. You can imagine if you're loading this plate system in the center versus on the corners, you may get somewhat different results. So it's important to understand that and the effect. And these, especially the bigger ones, you should definitely consider in situ calibration. So again, it's dependent on how the load is introduced. Ideally, you could apply test loads to the system in place and actually develop your calibration that way. Some of the smaller ones we can calibrate as a system too. So it just depends. If you imagine the gigantic plate system, you can't really fit it into a test machine. So it's best to be calibrated in situ. Next slide, please. So here's an example of a force plate used as a robot base. Imagine you could measure the reaction forces at the base this way. Say, well, why wouldn't you want to measure the forces right at the tool at the arm? Well, you might want to do both. But for example, if this arm is going to whap something with that red part, the sensor at the tool wouldn't see that, right? So for safety, you might want a reaction load measurement at the base. Now, if that arm's going to contact something, you could say stop it or reverse it or whatever. Also, you might be able to get a higher capacity measurement out of something like this, or for tip over, or various things you might want to measure. Again, these force plates require 12 channels. It's 3-axis times 4 sensors, so 12 channels. Next slide, please. Another reason you might want force plates is if you wanted a big through hole. So this is a design uses 4 of our round 3-axis sensors and 2 plates bolted to it, large through hole, as you can see. It's important that the plates aren't just any old plates. They should be machined flat and parallel, should be suitably thick. Height matching of the sensors may be required. Again, this is a system, should be understood as such, and obviously dig in on the details with one of our application engineers. But this is to plant the seed that these things are possible, and definitely something that's finding more and more interest in. Next slide, please. I'll pass it on to Ken.
Yep. Next slide, please. So we're going to give you a little bit of outlook on what's happening with multi-axis systems. Multi-axis sensors are needed to keep up with new technologies and application requirements. So as applications are changing, so are the sensors, and these are the best ones to move along with that new technology. Multi-axis sensors are better embedded into products, and that's because instead of using 6 individual load cells, you could use 1 to do the same work. Digitized sensor information allows for remote monitoring and increased analytics, and that makes it easy to access. You can access it remotely if you need to, or on site. You can have data collection, and then you could use that for analysis of, during the activity or at a later time. Multi-axis sensors track performance and reliability better than traditional sensors. And that's because there's more measurements in more directions. So I think that speaks for itself. And then lastly, smaller sensors with digital outputs are easier and less expensive to permanently install in machines. So maybe in the past, people have used sensors like this, perform their tests, and then taken them out and then put their machines in the field. Nowadays, you can integrate them into the machine and install them, test, and monitor the activities that are going on. Next slide. So this is from a system level perspective now. So evolving system health monitoring is important these days. It seems that more and more companies are measuring more and more data all the way across their applications. And as a result, they're collecting more data now and for future analysis. And what they want to do, of course, is to see, is the system performing as expected? And then maybe also analyze data to see if there's ways they can look and find ways to improve those processes as they're going on. So a specific use case is automobile company is collecting all sorts of data across their system, and is a issue comes up with a component, and so they could use this data to pull up specific events, activities that occurred around the manufacturing of this component, and maybe track it down now to a specific lot or specific serial number, so they can limit the range or amount of products that could be involved in a total recall. Next slide. How is interface leading the way into the future? Well, we're leveraging our 52 plus years of experience and utilizing it with, of course, our standard offering of single axis load cells all the way through our multi-axis load cells now. And a lot of the applications that we've been involved in the past are also now using multi-axis load cells, which Keith will explain as we move along. We're making customized sensors to meet our specific customer needs. So that's something we're real strong at. And so if you need any help, we've got a great team here that can help you through those application challenges. We're good with interconnecting systems, and our company as a whole is expanding our expertise with communication protocols like EtherCAT, CAN, Ethernet, and many others. Of course, Keith mentioned our BlueDAC math scripts, so that takes multi-axis load cell processing or data that comes in through our BX8 and allows you to do extra math calculations as needed to further understand your application's needs. And then, of course, intelligent data acquisition and standalone systems with onboard processing, and Keith shared a bunch of that with us with the BX8 and BSC4s, which allows, even in a standalone application for you to get more out of your testing and your activities. Next. Keith, I hand it back to you.
All right. Thank you, Ken. So structural testing is an interesting case. A lot of our customers do structural testing. Could be material testing, could be actual structural testing on a system such as an airframe or a rocket or a automotive related. So one of the things you can do with more data, multi-axis sensors, is to get a better understanding of the reaction loads at your boundary conditions. So a lot of assumptions are made when you're applying test loads. What are the reaction loads? Well, with multi-axis sensors, you can start to measure some of those, and that may be quite interesting. Usually there's more going on than the models or than you might say understand. Transmissive loads through the DUT are sometimes interesting too. So you've got the DUT mounted, you're applying test loads to it. What do the reaction loads look like at the other side of the DUT? Obviously bending and side loads, there's a lot of that going on. Our single axis low profile load cells are very good at, say, ignoring those, but they're present. So maybe you should actually try and understand what they are. Either you can use those to, say, refixture your tests so you can minimize them, or maybe they're just part of the data you're collecting. Again, you can look and see what the, say, the force vector is, the center of force. You're applying a load. If there's off axis or bending, that actually means the load isn't, say, vectored exactly how you might expect it to be. 6-axis sensors can help you understand that. Again, boundary load conditions. If you are, say, having simulations of your products, you may make a certain assumptions, right? Some testing you can do with, say, multi-axis sensors would be to validate or to understand the boundary conditions, and you can feed that data back into the simulations to get, say, better results. Also, expansion of existing testing methods. Again, if you're testing something, think, well, would it be interesting to have more test data? You know, some of these assumptions, are they valid? So you can, say, expand the scope of your test to include more parameters. Next case, please. Friction, this is kind of an interesting one. There's lots of ways to do friction testing, but this is kind of an example of how you could do it with sort of increasing numbers of axes in your measurement system. And so a single axis sensor, you can imagine you apply a weight to a specimen, and then you say drag that specimen across a surface. That drag force could be measured with the single axis load cell. That's great. Assuming the weight is constant, you're pulling, and you can see what the force is. Except, especially in this picture, it's very dumbed down. Imagine that whole thing would probably want to tip over when you pull it. So how do you keep it from tipping over? Well, you probably have some kind of guides or something, right? So those might create parasitic loads, may create non-repeatability in the system. You know, how do you constrain the system without, say, affecting the measurement? So another way to do it would be to, say, use a 3-axis sensor right above the specimen. Now you can use guides or whatever, it doesn't matter, because the sensor is actually sensing right at the test specimen. You can pull on it. Now you have a weight. Okay, you assume that weight's constant. Maybe this thing chatters a bit as you pull on it. And so you can actually have a data channel that shows the change in weight as you slide this. So you got your fixed weight, you've got your measured weight, and then you've got your friction force. They also tend to want to move side to side a little bit. You could get that force as well. Well, what if you add a 6-axis sensor? Now you can do all of the above, but also maybe measure, say, the tendency of the specimen to rotate as you try and slide it across the surface. Maybe that's great. Maybe you want to understand that, or maybe you just want to adjust your fixturing such that you don't have that effect. Maybe that, you know, affects the performance or the results of your testing. So again, more data allows you to understand more about what's happening and maybe tweak your test or just gather more data for analysis. Next slide, please. This is a case, it's interesting. There's a lot of cases that fall into this example, but I use propeller because it's one that I think is easy to kind of grasp. But you think of a single axis sensor, you've got its capacity, you've got tension and compression, and then you've got, you know, anywhere within its rated capacity. So you might calibrate it, say, only in compression if you're going to only use it in compression. Well, 6-axis sensor is similar, except it's got 6 axes, right? So are you going to be using the sensor throughout its entire possible range of operation? Or are you going to be, say, limiting the use to a certain subset of the potential ranges? And it turns out in most cases, you will be limiting them, but you may or may not know what those limitations are. But this is a good example. You'd say pretty certainly if the propeller, say, is only going to be spinning in the clockwise direction, right? So you're going to have a torque about the z-axis in only one direction, and then the thrust is going to be applied in only one direction. And then you could say, okay, probably F and Y are going to be pretty minimal. Probably the bendings will be there, but they may be somewhat minimal. So you can say, okay, FC in only one direction, MZ in only one direction, and then minimal. Of the other loads, you definitely want to measure them, but they're relatively small, right? So now all of a sudden we've defined a use case that we can actually apply a calibration to the sensor that's more similar to the use case. We say, what are these expected loads and what direction are they? And we can apply test loads accordingly during calibration. Again, that develops a coefficient matrix that's tuned more to the use case versus just a more general purpose. condition where we don't know what the customer might be doing with the sensor. Moving on to the next slide, please. I always like this example. It's pretty interesting, really. It's seat testing, seats, furniture, couches, automotive seating, aircraft seating, everything gets tested. They're actually testing standards, and also it's, testing for durability. Might have a simulation where somebody sits in the seat and gets back up and sits down, hundreds of thousands of times, simulating, the entire lifespan of the seat. I'm saying a taxi or something where people are getting in and out, in and out, in and out. So they do that with a test. Imagine as the seats break down, the cushioning changes. If you're applying load, say with a single axis sensor, you're assuming the loads are all on axis. There's actually usually quite a bit more bending than you might understand. In this example, you can see there's a little fixture in the end. This might simulate somebody's shoulder blades or somebody's rear end. Imagine as it connects or impacts or touches the seat, it's going to actually not load it uniformly. Usually, it's going to load it more on one edge than the other. Then, as you push it into the seat cushion, the loading may move around, right? And so, what is that? That may actually affect the results of the test. It also may be damaging to the load cell. But if you don't know what it is, how do you know how to prevent it? So one way is just upsize a load cell. So maybe you break a load cell because there's a lot more bending going on than you realize. So you upsize the load cell, you break another one, you upsize. So now you've got a giant load cell to make this measurement. So you're measuring 500 pounds with a 2,000 or a 5,000 pound load cell. Well, maybe you could readjust your fixture and get rid of the bending. So 6-axis sensor can tell you what are these bending loads. Also, hey, maybe they're important for the test. Instead of trying to get rid of them, maybe there will be these loads. You want to measure them, characterize them, and use those to make sure your tests are more repeatable, right? If you're trying to say test 2 different seating arrangements or different foam structures or whatever, you might want to repeat the loading so it's the same, so you can actually get apples to apples comparison. So if you're applying, say, a lot more twisting or something to one of the specimens than the other, hey, one may wear out faster than the other, but you don't really know why. Something like a multi-axis sensor can help with that. So there we go. I think we're back to Ken now.
Yes, now we're going to go over some frequently asked questions. Keith and I'll answer these together. What if I only want to measure 4 axes? Well, the good news is you can measure 4, but you'll probably be doing it with the 6-axis load cell. And as we found out, a lot of times having the information for the other 2 axes may just come in handy. So standardly it'd be a 6-axis load cell being used for that application. Why do you want to know the geometry of the loading, Keith?
Yeah, good question. As we discussed in one of the use cases, if we know the geometry, you can start to understand what the actual loads are that the sensor sees, and might be able to calibrate it more under those conditions. Also, we're going to try to make sure the sensor is sized appropriately. Sometimes there can be a lot more bending loads than may be immediately apparent. And so we want to size the sensor appropriately. Really need to know not only what the forces are, but what is the geometry? Where are these forces being applied? Are they being applied to the top surface of the sensor? Are they being applied at some distance? What does this fixturing look like? Is the fixturing going to bend as you apply the loads? All of those things come into play. And so we want to understand those. So usually we want to see a sketch. Can be dumbed down if it's proprietary information, or we can get very much in detail if you're willing to share. But what we would do is look at where are these forces applied? What does the loading hardware look like? What are the the lever ratios and all that goes into what we want to understand when we make a recommendation on the sensor.
Good. Do I need to do math? Well, on a 3-axis load cell, they're just 3 full bridges. So there's no math or no matrix involved with that. On the lower capacity 6-axis, there is matrix math involved, but if you purchase the BX8, it's pretty simple. The instrument can do all the internal math for you. Basically, with a point and a click, you load the matrix coefficients into the system, and you basically load the sensor, and all that math is done for you, and you even get scaled analog outputs to match. In a force plate or a high capacity, 6-axis. You may be required to do some math externally, depending on if you're going to take the signal outside of the system. But if you're going to use our BlueDAC software, you won't need to do the math. It'll be calculated, and the measurements will be displayed on the screen through the BlueDAC software. Let's see, number 4. Is there a single signal for each axis, Keith?
It depends on the 3-axis sensors. Many of them are quite similar to, 3 single-axis sensors, in that there's a signal for each axis. So FX has its own signal, FY, FC, etc. On the 6-axis sensors, that is absolutely not the case with our sensors. They all have signals that change with any loading condition, and those signals are measured independently and then multiplied across the coefficient matrix. So depends, but the answer in general with the 6-axis sensor is, our 6-axis sensor is no. You have to measure all of the signals and then calculate your applied loads.
What instrument do I need? Well, as we've shown in this presentation, with a 3-axis load cell, a BSC4 is good. A BX8 would also be great. With a 6-axis load cell, the BX8 would be great. But really, it comes down to what your needs are in your application. We have many, many options and experienced applications engineers that can help you to help solve your total solution. So best to come to us, give us your challenges of your application, and we'll help put together the right instrumentation to go with the load cells to get you the results that you need. Can they be environmentally rated, Keith?
Yes, indeed. Need to know that ahead of time. Some of the sensors lend themselves more to it than others. You imagine some of the very low capacity sensors, such as a 2 Newton. If you fill that thing with potting, well, it becomes a 10 Newton sensor. But so some of the sensors, the sealing will affect their performance, and the answer would be no, they cannot be sealed. Some of the bigger ones are relatively insensitive to that. They can be filled with potting, filled with gel, sealed, whatnot. So we can provide up to, say, IP68 rated, so for short-term submersion. But again, it's dependent on specifically the sensor and the application. What's the material or the substance it's going to be exposed to, those kind of questions, temperature ratings, things like that we'd want to discuss in detail before we actually made the recommendation.
Do I have to use all the mounting features? Well, we recommend that you do. And the reason is that that's the way we test them in the factory. And so we want to make sure that your results match our results. Keith, do you have any insights on that you want to add?
Yeah, especially when you're talking about like mounting holes. Some people say, oh, if I just use 3 of the holes, I'm going to only be pushing on it, so I don't need to keep it, from coming loose. I'll just use 3. Well, okay, but we definitely do not recommend that. You're not duplicating how it's calibrated. You may have performance issues. They're hard to quantify. You just get wrong answers in your measurements. You don't necessarily know that you're not getting good results. So again, there's not just extra holes for the heck of it. These things have a certain number of mounting holes, and they are intended to be used. Next slide, please. Or next slide. Next question.
Next question, Dan. There we go. How do the overload ratings work? Keith, I'm going to just defer this one right to you.
Well, the 6-axis and 3-axis sensors are designed to allow loading to their full capacity in each axis simultaneously. And that may be different from other sensors, even other sensors that we sell. But these 3As and 6As we've been talking about can all be loaded to their full rated capacity in each axis simultaneously. But they also have safe overload ratings. You have to be careful. Those are reserved for accidental use. You don't want to say, oh, it's okay to load up to, say, the 150% safe overload in the Z. That's not safe. The safe overload is reserved for, say, accidents. And if you, say, use all of that, well, you have nothing left over for accidents, or even if you don't know exactly how much load you're applying, right? And so it's very important to observe the limits of these sensors. And if you have any sort of outside use cases that may want to load them outside of their capacity, you definitely need to dig in deeply with your application engineer and understand exactly what's going on before we would say that it's ever okay to load them above their capacity. Next slide. Next question.
And Keith, what is the frequency response?
Again, difficult question. These are quite stiff, so they can be used in, say, higher frequency response requirements or measurements with higher frequency response requirement. But that said, the system response has a lot to do with everything that's mounted to the load cells, the mass of the plates, the inertias, whatever. So typically it's not going to be thousands of hertz, it's going to be hundreds of hertz. We have customers who use these successfully in that range. But again, it really depends on the entire system. So the reason the question's on here, because you may notice there isn't on the data sheet, there isn't a frequency response specification. And there's a reason for that, because it cannot be defined without evaluating the entire system.
And do your 3 and 6 axis sensors have internal electronics? I can answer this one. The answer is no. They don't come with internal electronics as a standard. So they're millivolt per volt outputs, and so strain gauge beams. And but if your application has a need for, let's say, an internal amplifier on a 3-axis load cell, or maybe CAN bus on a 6-axis load cell, we may be able to accommodate that. So it depends on your specific sensor need and the requirement of your application. Next slide. Jamie, we'll pass it back to you.
Sure thing. Thank you, guys. That was great and very good information. The technical expertise you shared, I think, is going to be really important to everyone. And again, we'll have this recorded presentation available on our website. Keith did have a question, another Keith for Keith. They want to know, he was curious how you calibrate the multi-axis sensors and if there's any photos or videos of the calibration that you can share.
Hi, Keith. Yes, it depends. Small ones are calibrated with plates and weights. Larger ones are in test machines with, again, fixturing to be able to apply simultaneous forces and moments. And then also possible to use an automated machine that applies combinations of loads all simultaneously. But in the very, say, the typical case or general case, usually they're applied 3-axis just with single axis loads applied, or the multi-axis, or I'm sorry, the 6-axis sensors, sort of single combinations of a force at a distance. So a force and a moment load applied simultaneously, and then another pair, but not necessarily all axes calibrated simultaneously. And can we share some pictures and videos potentially? We do that offline, but yes.
All right, great. We don't have any other questions so far. If you do have a question and want to use the chat feature, please share. And definitely, this is an opportunity to engage with our application engineers and experts in-house. We see a lot of different use cases, and certainly happy to share what we know and through our own experiences, what we think works best based on your requirements. So be sure to reach out to us. We're here to help. This presentation will be available on our website. Again, we'll do a recap. We'll send that out to you along with the video. And with that, you'll have access to all the information shared, as well as be able to see whether or not, or see all the other videos that we've prepared for you this year. We've done, this is about our 6th or 7th event. And there are no more other questions. We'll stand by for another minute or two, but we want to thank you all for attending. We appreciate your participation and look forward to having more conversations in the future. Thanks, everyone.
Thanks for attending.